Hello, I'm Michael Melatti, a student at Georgia Institute of Technology, and today I'll be presenting the paper KeyDrown, Eliminating Software-Based Keystroke Timing Side-Channel Attacks. This paper was a combined effort from the original authors, Michael Schwarz, Moritz Lipp, Daniel Gruss, Samuel Weiser, Clémentine Maurice, Raphael Spreitzer, and Stefan Mangard. The original paper was presented in Networks and Distributed Systems Security, NDSS, Symposium 2018, San Diego, California. With that, we can jump right in. This paper focuses on keystroke timing attacks, which infer typed words, passphrases, or created user fingerprints from very precise keystroke timing events. In this paper, the authors present two new attacks that allow malicious actors to recover keystroke timings, exposing risk to users. Additionally, the authors present a countermeasure and implementation of a tool called KeyDrown to thwart this type of attack. So, what is a keystroke attack? This type of attack in general aims to monitor when a keyboard input occurs with very precise timings, which in turn allows a malicious actor to statistically infer user input, such as passphrases. To make matters worse, a malicious actor can often acquire many traces of, say, keystroke timings of a particular word, phrase, or combination of keystrokes. This is to say that a user can often enter in the same passphrase on multiple websites multiple times a day, which gives an attacker ample opportunity to capture multiple events and those chains of events. In this way, keystroke timings are very valuable to malicious actors, and typing data can expose a lot of risk to users. In the past, malicious actors could directly gather information through sensor data from, say, an Android device. However, lots of previous efforts have been made to reduce this risk. However, this still leaves the door open for side-channel attacks. And to elaborate on what side-channel attack is, it is a weakness in the compute system, not the actual algorithm. An example of this would be to say a weakness in an algorithm would be a cryptographic algorithm that could be exposed. In the case of keystroke timing events, microarchitectures allow monitoring memory access with fine granularity on single cache lines. This is a very difficult problem to solve, as you can see, because unlike, say, an attack on a cryptographic algorithm implementation, you can't fix this by just changing the algorithm or correcting the algorithm. With the keystroke timing attack, you have to defend a long path of independent secret data, all the way from the user inputting data on the keyboard, up through the hardware interrupts, shared libraries, and up through application and user space. So there's a long path that this data travels and a lot of ground that you have to cover to protect the user. Before we look at the attacks that our authors implemented, it's useful to first look at what a keystroke is. A keystroke is a non-repeatable low-frequency event. When you press a key on a keyboard, there's an interrupt that gets sent to the CPU core, and then there's some code that's executed on the OS driver, and the preprocessed input is sent forward to the user space library, which identifies which window the keystroke should be sent to. You can see by this description that there are many avenues for a malicious actor to attack. In the past, previous defense mechanisms aimed to restrict access to system interfaces that provided these interrupt statistics. This is not enough, however. Our original authors provide two examples of attacks on systems that have these securities in place. The first attack uses RDTSC instruction to determine the execution time of the interrupt service, and then they just determine if the interrupt was caused by a keyboard. The second attack that the authors implement uses Prime Probe, and they implement an attack called MultiPrime Probe attack on the kernel to determine when a keystroke is being pressed in the kernel. The first attack presented by the authors is the low requirement interrupt timing attack. This utilizes the RDTSC instruction in the implementation to monitor differences in the execution time of acquiring high precision timestamps. Small differences would allow a malicious actor to infer CPU utilization, but the larger differences indicate that the measurement process was interrupted. I/O events, like keyboard interrupts, lead to clearly visible peaks in the execution time due to the interaction of keyboard interrupt service routines with hardware and subsequent processing of the keystrokes. Additionally, modern operating systems have core affinities for threads and will continuously be interrupted by every keyboard interrupt, making this attack surprisingly reliable. On the slide on the left, we can see the algorithm that the authors implemented. It calls the RTSC instruction and compares the current timestamp to the previous one and gets the difference and uses a threshold for identifying keystroke events. On the right side, we can see a graph that the authors provided in the paper that has clearly distinguishable peaks that directly correlate to keystroke timings. In testing, the authors were able to directly identify test subjects as they typed in the search bar and identify URLs that they typed with high accuracy. Additionally, this attack was just the basis for a more elaborate attack that the authors also implemented using JavaScript embedded in websites. The authors in the paper also present the MultiPrime Probe attack as a keystroke timing attack. This is a cache side channel attack where the attacker monitors the victim's cache by measuring the access time of how long it takes to measure an address. One can then infer if the address has been loaded into the cache or not. And additionally, the attacker can use specific instructions to remove addresses from the cache. In the Prime plus Probe attack, the keyboard focuses on the interrupt handler with the kernel. The attack targets the code in the keyboard interrupt handler that is executed each time a key is pressed. Thereby, keystroke events can be inferred by observing cache activity in the cache sets used by the keyboard interrupt handler. The authors improve upon Prime plus Probe with their attack called MultiPrime plus Probe, which combines information from multiple simultaneous Prime plus Probe attacks on different addresses. Keystroke events cause higher activity in the targeted cache sets and thus produce clearly recognizable peaks for every key event. The MultiPrime plus Probe advantage is that the multi-pronged attack can reduce system noise, providing the malicious actor even greater accuracy in the attack. In the graph below, we can see the clearly distinguishable peaks that directly correlate to keyboard key press events. Before we can get into the implementation of the countermeasure, we have to first look at the requirements to mitigate the attack. We can make some assumptions about our attacker. First of all, the attacker has some cards up their sleeves. They are granted unprivileged code execution and can continuously monitor a side channel to obtain traces of all user input. The attacker would also be able to obtain multiple traces of a password attempt. For user input, you can't force a user to enter the same thing 300 times to identify usage, but you can expect them to enter their password a reasonable amount of times. Our first requirement, our defense must minimize side channel accuracy to an acceptable rate, not provide more accuracy than an always-on oracle. Secondly, we assume that an attacker will have multiple traces of the attack, and an effective countermeasure must make the number of traces required to infer user input to be impractical. Studies have shown that people have 1 to 5 passwords and enter 5 passwords per day on average. Additionally, users change a password on average every 6 months. This means that we can assume attackers can obtain 913 traces of a password over its lifespan. Our countermeasure, again, must make it the number of traces required to infer user input to be impractical. Thirdly, as a requirement, the countermeasure itself must be secure and not open the door to additional side channel attacks. This was not mentioned in the paper, but as an additional requirement, the countermeasure should be performant enough and shouldn't infringe upon the user typing experience. In the past, great strides have been made to protect the user data and data around user input. However, as we've seen from these previous attacks, there still exists these side channels where malicious actors can get this information, and it exposes high risk to users in their input. In coming up with a countermeasure, our authors considered a lot of possibilities, and there were some clear winners and losers. Some things that wouldn't work is disallowing unprivileged access to statistics/APIs. The reason this wouldn't work and wasn't considered by our authors is because other side channels still exist. Additionally, considered and deemed not effective would be to restrict high-resolution timers such as RDTSC and perf. The reason this wouldn't work is because one can always build their own high-precision timers. The acceptable solution that our authors came up with and what the countermeasure is based on is solving the problem by injecting fake keystrokes. Note that this type of solution wouldn't work well for other side channel attacks because you could trigger an event multiple times and average out the noise. However, this type of approach will work well specifically for user input. The solution and countermeasure presented in the paper is called KeyDrown. KeyDrown injects fake keystrokes right at the beginning with a keystroke interrupt, and the event travels up through the entire stack, covering all points the attack could possibly observe the event. Additionally, a real keystroke replaces a fake one. Thus, an attacker cannot simply discover a pattern of fake keystrokes because our keystrokes have uniform density. KeyDrown is broken down into 3 layers. KeyDrown in the first layer is implemented as a kernel module that handles the hardware interrupts from the input device and timer interrupts. For timer interrupts, it injects a keyboard interrupt. If it observes a keyboard interrupt, it injects a non-periodic one-shot timer with a random delay. For real and fake keystrokes, both interrupts occur. Additionally, KeyDrown Layer 2 is used to protect against flush plus reload attacks and prime plus probe attacks. We didn't previously talk about flush plus reload attacks, but they're very similar to prime plus probe attacks, except they require shared memory. The prime plus probe attack is similar to a flush plus reload attack, but does not require shared memory, but is often noisier. Our authors presented MultiPrime plus probe attack, which cuts down on the noise. Back to KeyDrown Layer 2, real and injected keys should have the same code paths and data accesses to the library. KeyDrown Layer 2 uses uncommon keystrokes like media popping events, where it is possible the code will pass through the library and has likely different code paths through the library. KeyDrown duplicates these keys to a character and sends it to a different window. Both events travel through the user space library simultaneously, covering all code paths without actually going to the application. This covers all paths an attacker could use to identify if it was a real or a fake keystroke. To break this down further, real and injected keys, or fake keys, should have the same code paths and data accesses to the library. Injected keys, or fake keys, are valid but are typically unused keys. Duplicate keys randomize their values and send it to a hidden window. KeyDrown Layer 3 protects the actual password entry. This layer must protect the buffer itself, where the password is stored, because an attacker could mount a prime plus probe attack on the buffer. A countermeasure to this is to generate the same cache activity on the cache lines used by the buffer, independently if it receives a real or fake keystroke. Our authors very carefully evaluated the effectiveness of the countermeasure using the F-score to get statistical information on true negatives, true positives, false negatives, and false positives. The authors compared the accuracy of the side channel while KeyDrown was on and not on. and they compared the F-score of the always one oracle and random guessing oracle. We would want the attack to yield no additional information by using the side channel. Here we can see graphs from the evaluation. On testing, our KeyDrown countermeasure on and off. On the left side, we can see the test done without KeyDrown countermeasure in effect. The attacker is able to very accurately guess keystroke timings. On the right, we can see an example with the KeyDrown countermeasure turned off, with a very low F-score. Additionally, we can see the results from the prime plus probe attack. Again, on the left, we can see where the KeyDrown countermeasure was not in effect. And again, an attacker would be able to very accurately guess keystroke timings. And on the right, we can see the KeyDrown countermeasure turned on. And again, we see a very low F-score. Additionally, to stress test the effectiveness of the KeyDrown countermeasure in our evaluation, the authors additionally created a scenario with an incredibly strong attacker that had additional information. The attacker was granted many advantages that would be very unlikely in a real-world scenario. Some of these advantages included small variance in trained text sequences. Additionally, they were given exact location of text sequences. This is the exact start and stop of a passphrase. This still required 2,458 traces for an attacker to be able to identify a passphrase. Earlier, we stated that an attacker would have just over 900 traces of a passphrase, as a user frequently changes their password every 6 months. So this number of 2,458 traces is well beyond what an attacker would be expected to be able to obtain, effectively making our countermeasure showing its effectiveness. Additionally, to the implementation of KeyDrown, the KeyDrown countermeasure, we had previously discussed 3 requirements. The first requirement being lowering the accuracy, and second requirement requiring an impractical number of traces for an attacker to glean information from an attack. The third requirement that we mentioned was making sure the actual implementation itself was secure. Here we have to look at the 3 layers of KeyDrown. The first layer is the kernel layer, and this can only be attacked with a prime plus probe attack. And here, the real and fake injections are the same. This does not expose additional information to the prime plus probe attack, thus making this layer secure. In the second layer, we protect the user space library. The second layer does not know if an event has been real or fake, so no additional information can be gained here by an attacker. This also applies to the third layer, because the cache activity stays the same. So as we can see, in all 3 layers of the implementation of KeyDrown, our implementation is still secure. Additionally, the paper analyzed the performance of KeyDrown. The authors saw a 2.5% performance overhead on some devices, and an increase of battery consumption of up to 4.6%. The KeyDrown implementation was tested on Linux x86-based architectures, as well as some Android devices. We definitely recommend you try out the KeyDrown countermeasure for yourself. The authors of the paper have graciously provided all of the source code for the KeyDrown countermeasure, which you can download off of their GitHub. The link is provided on the slide. To test, you'll either want to have an Android device which is supported, or you'll want to spin up a VM using the Ubuntu version 16.04. The README on the GitHub page includes instructions for installing from binary for the x86 architecture. Once you spin this up, you can see the KeyDrown countermeasure in action for yourself. You can monitor keystroke events happening from the /proc/interrupts. You can watch this with the watch command. Instructions are included for this on the README, and you're able to see with KeyDrown turned on, this will auto increment, and with KeyDrown turned off, you'll be able to clearly distinguish individual key presses. In this slide, we're seeing a VM that we've spun up. This is running the Ubuntu 16.04 version mentioned earlier. We can see in the application, when we type, we can see individual key events coming into the application. By turning on KeyDrown, we now see the auto-incrementing effect of KeyDrown, so we know that it's working. Again, all of this can be downloaded and tested off of the author's GitHub page. Wanted to finally conclude by thanking the original authors of the paper. It was a very fascinating and interesting topic. I would definitely implore everyone to check out the paper and check out the GitHub and try running KeyDrown for yourself. And thanks again to all the viewers for sticking it out to the end of the presentation.